So far in this topic, we've looked at surds and we've looked at indices. Okay, and what we're going to do now for the next couple of weeks is try to tie some of these fundamental skills in with some graphing. And the graphing we're going to look at is exponential functions, which is a really topical graph at the moment because you would have all seen this particular thing in the news, the so-called flattening the curve strategy on COVID-19. And really what we're looking at is how would we flatten this curve? And you'll be able to actually work that out and talk about that with confidence at the end of, say, the next week or so. So let's start to explore this by looking at a particular exponential function, y equals a to the x, where this a value we're going to say is 2, or our base of the exponential function is 2. So 2 to the x is an example of an exponential function. Now, the first thing to note about exponential functions is that they curve. They're not straight. Okay, and exponential functions are really the first function that we've seen that have a curved pattern rather than a straight line graph. And that has particular relevance when we graph this function down here, but we'll talk about that in a sec. So the first thing we're going to do is complete a table of values. So we're going to sub these x values into this function, and I'm going to start with 1. So I'm going to say that I want to find out what y is when x is equal to 1. Well, that's 2 to the power of 1. That's easy. That's 2. And now let's do 2. Y equals 2 to the 2, which is 4. Y equals 2 to the 3, which is 8. And y equals 2 to the 4, which is 16. All right, what about 0? Y equals 2 to the power of 0. The 0 power rule says that anything raised to the power of 0 is 1. Fits the pattern as well, doesn't it? Okay, this doubling concept. All right, what about negative 1? Y equals 2 to the negative 1. Well, according to the negative index rule, what I can do is grab that and put that, if it's over 1 at the moment, I leave 1 in the denominator, grab that and put it into the denominator, and it becomes positive. Okay, and just to review that, essentially what we're doing here is we're multiplying by 2 over 1 and 2 over 1. Now, common bases, add the powers. That's 2 to the 0. 1 times 2 to the 1 is 2 to the 1. What is 2 to the 0? Well, that's just 1. 2 to the 1 equals 2. So that's why we're allowed to do that move. So 2 to the negative 1 is actually a half. 2 to the negative 2, hopefully you can see, that's y equals 2 to the negative 2. Y equals 1 over 2 to the negative 2. 2 to the positive 2, whoops, 1 over 4. And maybe you can see what's going to happen here. That's going to be an 8th, and that's going to be a 16th. If you're not too sure, pause the video and try those out by substitution to make sure that you know how those values have come about. Okay, so now what we're going to do is plot this graph. So we're going to do our very first exponential function. Excited? Well, I am. Okay, so let's plot this point here. When x is 0, y is 1. That's the y-intercept. When x is 1, y is 2. When x is 2, y is 4. When x is 3, y is 8. When x is 4, y is 16. And we can see there we've got the makings of our first exponential function. Right, negative 1 is a half. These are a bit harder to plot because they're so small. Quarter. And it's going to get closer, an 8th, 16th, 32th, etc., etc. Right, so what I'm going to do is do my best here. So I'm going to do my best. Okay, I've noticed what some students do is they grab a ruler, link them, link them, link them, link them, etc., via straight lines. This is an exponential function. It needs a nice smooth curve to connect all of these things. So I'm going to sketch it and then I'm going to critique my own work and give you a few tips. Right, so here goes. Bad start. Okay, now I am not drawing this on the screen, for those of you wondering. I'm drawing it on a pad on my desk, and it's hard to draw this with a pad. Right, so we're going to come down through that point, This is coming all right, through the y-intercept, through a half, And what we've got to do now is get closer and closer and closer to the x-axis without actually touching it. Oof, that end was awful. Okay, so some critique. No. Okay, exponential functions don't hit the or get close to the x-axis and then bounce back and then bounce forward again. It's got to be smooth, so it's gradually got to get closer and closer, but it can't come out and in. All right, so it sort of bumps in, bumps back out. So we've got to remove, or you guys have got to remove some of the bumpiness. See this sudden move here? No, it's got to be a nice clean curve. So those of you who sketch this in pen, I would say are fairly cocky. Okay, you back your own ability, which is great, but very rarely do I get an exponential function right the first time. So I would be sketching this in pencil and make your mistakes, then rub it out and keep correcting it until you get this nice clean curve. This little bump, no, don't like that. Clean curve, it should go through that via a clean. The rest of this looks okay. All right, as usual, we're going to mark our key features, which is the Y-intercept. And now we're going to describe what happens. Describe the shape of the graph. We're going to say when x greater than 0, values of y increase rapidly. Okay, when x is less than 0, values get closer to 0 as x decreases. Okay, so what's happening here is it's greater than 0, these y values start to kick or really jump fast. Okay, exponential growth. Okay, but as we get less than 0 here, what we're going to do is get closer and closer to 0. Mind you, we're never going to get to 0 because whatever x value you give me, say you go, hey, Mr. Miller, here we go, sub in negative 100. I bet you that's going to get to 0 finally. Let's do it. Y equals 2 to the negative 100, which is 1 over 2 to the 100, which is 1 over a really big number, which is 1 divided by a really big number is a very small fraction, okay? But it's 0.00000 something, and then like a 1 or something. I'm just making this up. What I'm saying is it is a number, very small, very close to 0. But if you said, is it 0? The answer is no, it is not 0. Does the graph have a y-intercept? Well, yeah. And its coordinates, as we established earlier, are 0, 1. Does it have an x-intercept? No, it does not. And the reason for that, okay, is that 2 to the power of x is greater than 0 for all x. Okay, so any x value you give me, it's going to be above 0. So 2 to the power of any value will always be larger than 0, no matter what. Okay, so therefore it will never reach the x-axis. All right, so here it is more formally. Okay, so here's the function of y equals 2 to the x, and that's what your curves really should look like. That's a computer-generated one, so it's really nice. But yours should look like that. All right, we can also have this situation where we graph something like y equals 0.8 to the power of x. Now, this a value here causes this particular phenomenon to happen. And actually, that's what the Australian government are really trying to do with this COVID-19 curve is, instead of having like a graph of or a base of 2, that would represent each person giving the virus to 2 other people, they would love it if they had this situation, whereas every person gave it to less than 1 person, because what will happen is the virus will die out. I mean, ultimately, this is what they want, 0 to the x, y equals 0. Okay, no virus, but this is the situation they're pulling for, and that's why we're socially isolating at the moment, is it'll slow the spread. We want this growth rate, or this a value, to go less than 1. Okay, so that just summarizes that. We get an exponential increase as a is greater than 1, or an exponential decrease when the value of a is between 0 and 1. So some more notes there if you want to read exactly what's going on. This is a really important thing here. So the horizontal line with the equation y equals 0 is called the horizontal asymptote. Okay, so that's a new mathematical word there. Okay, now what an asymptote is a line which a function approaches but never quite gets to. Okay, and what I'd like you to do is on these graphs over here is put your asymptote in. So this is the line of asymptote here for the function y equals 2 to the x. It's got to be dead on the x-axis. That's in fact the line y equals 0, and it must be labelled with its equation. Over here we've got the same thing. So it's got to be smack bang on the line. I know many of you won't see it, but draw it in pencil and label it y equals 0. So you see some pencil marks there. This first function that I drew here, I can now add my asymptote along the line and label it with its equation y equals 0. Okay, so the asymptote is drawn as a dotted line and labeled with the equation check. Okay, so here's some examples now. So what we're going to do is graph the following functions on the same set of axes using the class pad and sketch in your notes. Okay, so we've already looked at y equals 2 to the x, but we're going to slam it on this Cartesian plane here. Now this is going to be extremely difficult for me to do with this, what do you call it, this pad I've got here in front of me. So I'm going to try and do it with some software and show you what happens. All right, so this is a program that we teachers use called f of x. And I'm just going to get it to match the scale, which I think was -4 to 4, -200 to 200. Okay, and the first function we wanted to graph is y equals 2 to the power of x. And there it is there. Notice that the program has already put or recognized that it's got a horizontal asymptote. So you want to sketch that one in along there. And again, do your best to sketch those points, but the highest value is 16, and that's here. Okay, so it's going to look like it's not rising quickly. 2 to the x is a fairly quick rise, but compared to some of these other ones, you'll see the difference. Right, the next one you want to sketch is y equals 4 to the x. So y equals 4 to the power of x. Here is the function here. So it's got this massive kick, okay? And that again is like the virus, you know, for each person who gets it, giving it to 4 other people, who give it to 4 other people, who give it to 4 other people. You can understand that we're going to get this massive growth, okay? So yeah, that's that one. Now remember, you can get those key points on your calculator simply by going say 2 to the 4 to the power of 1, 4 to the power of 2, 4 to the power of 3, and 4 to the power of 4. So subbing in those x values and then plotting the points, okay, and then doing the same for the negative ones. Although again, you can see that it's going to get extremely close to 0 very quickly. All right, then we've got y equals 3 to the x, which should be somewhere in the middle of those. There it is there. Right, and then we've got some variations on this 3 to the x function. So this is what we call a reflection. So this negative here will be the same thing, except what it will do is drop a negative sign before every value. Now, see if you can predict what's going to happen here, but I'm going to type it in and show you -3 to the power of x. And there's our function there. And you can see here, this is y equals 3 to the x, and this is y equals -3 to the x, okay? And what it does is it just takes each point here and reflects it in the x-axis here, because instead of being positive here, it drops a negative sign in front of it, which sends it down to there. Again, use your calculator to get those points if you're not too sure how the program has done that, and you should find that your shape ends up something like that. Okay, now this one here, what this negative sign does in front of the x is actually means that when you sub in, like, say, -2, it means it's -2, which is actually 2. So this will be 3 to the power of 2, which will be like 9, okay, somewhere over here. And what happens is that it will take this graph here, this pink graph, 3 to the x, and it'll actually reverse it in the y-axis or reflect it in the y-axis, okay? So that one's going to be, let's graph it, y equals 3 to the -x. Just better wrap some brackets around that just in case. Right, and you can see there, this grey graph here is a reflection of this graph here. Okay, so what it does is instead of the positive values being the ones that kick, it's the negative values that have the kick, and it's the positive y values, or positive x values rather, that get closer and closer and closer to the line y equals 0 or the x-axis. Right, so pause the video if you haven't already and sketch the rest of your functions, making sure that you label that Y-intercept. It's going to be the same for all functions. And yeah, unpause it when you're ready to go. All right, so the last thing we're going to do is find the intersection of the graphs y equals 2 to the x and y equals 8, algebraically and graphically. Right, I love algebra, so I'm going to do it algebraically first, okay? So the intersection is when both of these functions are equal. So what I'm going to do is equate them. Now I've got y equals 2 to the x and y equals 8. So if y is equal to 8, what I'm going to do is replace that y with 8. And you'll recall, hopefully, by equating the bases, that this is fairly easy to solve. So I'm going to write 8 as 2 to the power of 3. And with equal bases, what we get is a power that can be equaled as well. So x is 3, okay? So what's going to happen at 3, 8? Now, how did I get that 8? I either subbed 3 into this, which is 2 to the 3, which is 8, or I knew that the line y equals 8 is just a straight line there. So it's going to intersect at 3, 8. Now let's do it graphically. So it's going to be, so I'm just going to sketch 2 to the x first. So 1 is going to be 2, 2 is 4, 3 is 8, 4 is 16. All right, it's going to come down here, through there. Okay, that's horrible. That bump's no good. Okay, there's a few issues with this graph, but again, accept my apologies. All right, make sure you slam in your asymptote. Have a few practices of saying the word asymptote as well. It's a kind of fun word to say. Y equals 0. Okay, stick your y-intercept in. Now we're going to sketch the line y equals 8. That's just this horizontal line here. So it looks like, so this is y equals 8. It looks like they intersect at this point here, which is, well, that looks like x equals 3, and that looks like y equals 8. 3, 8 is the intersection point. So there it is graphically, but a much better way to do these ones is to solve them. So now what I'm going to get you to do is work through the exercises, or exercise 3J, and we'll hook back up shortly to talk about the next part of the lesson.